Hello everybody, and welcome back to another geometry lesson. Today, we're tackling section 2.4. That's right, this is where stuff gets real. So, the first thing I want to mention is, in general, 2.4 is the beginning of the end of the unit. That is to say, the start of 2.4 is about going to be the same level of difficulty as 2.1 to 2.3. But near the end, it's going to ramp up. And that will only continue to ramp up as we go through 2.5 and 2.6. So please, do your absolute best to follow along and try these examples. With that said, let's get started. I want us to go back, all the way back, to when we first learned how to solve equations in middle school. Possibly Algebra 1. If I gave you the equation x minus 5 equals 17, and I asked you to solve this, how would you do it? Well, most people would remember that we can add 5 to both sides. And then when we do that, we end up with x equals 22, which, don't get me wrong, that is correct. But I bet that if I asked 90% of people, okay, what says that you're allowed to do that? Why could you add 5, and why did you specifically add it to both sides? Most people would have no idea. Geometry is more a study about the why than the how. So we are going to be invested in why this works and how we can apply it to other problems. This is given to us by a property of equality. A property of equality is just some general rule that all things with an equal sign follow. The first one is the addition property of equality. The addition property of equality says you can add the same term to both sides of an equation. Why are we allowed to do that? Well, it produces what we call an equivalent equation, an equation that has the same answer as the original. So let's go back to that example, and I want to show you how you might see this problem written out in a geometric sense. You could very well see x minus 5 equals 17, but in a geometric sense, you might see it written horizontally like this. This is the same thing as if I added 5 down below. It just looks a little bit weird because we're not used to it. Either way, the rule says that we're allowed to add the same term to both sides of an equation. Keep in mind, the only reason why we added 5 is because negative 5 and 5 would cancel out, giving us x equals 17 plus 5, or x equals 22. You can add whatever you want to both sides of an equation, and it'll still make it the same. The same goes for the next 3 properties. So we had the addition property of equality. You could add the same term to both sides of an equation, but it turns out it works for subtraction as well. The subtraction property says you can subtract the same term from both sides of an equation. So maybe I gave you the problem x plus y equals z. Ooh, didn't say that it had to be, actually let me write this out slightly differently. I didn't say that it had to just be numbers. This property works for any term in an equation. Keep that in mind. So, for instance, if I wanted to get x by itself, I could just subtract y from both sides. What would my answer be? Well, y minus y cancels out, so our answer is x equals z minus y. For brevity's sake, I'm not going to write out the rules for multiplication and division, but as you guessed, it's the exact same. You can multiply the same term from both sides, and you can divide the same term from both sides. So if I gave you x over 2 equals let's put 1 plus z. You could, for instance, multiply both sides by 2 to make that work. That's allowed. And if you have division, or sorry, if you have something like this, let's say we have, let me think of a good one here. Let's say we have xy equals 2z, and you want to get x by itself. You could also divide both sides by y. Bam, bam. The one rule that we might not be so used to is the substitution property of equality. Let me give you an example here. Let's say I tell you that some number x is equal to 5. Let's say I also tell you that some number x is equal to some variable y. Well, we can conclude that if x equals 5 and x equals y, then x, 5, and y must all be the same thing, right? So the substitution property says that we can replace an x with a y, or we could replace an x with a 5. Either way, we're going to get the equation y equals 5 or 5 equals y. That's the substitution property. When your variables match, or when just one side of your equation matches, you can substitute. I'll give you another example. Let's say that 17 equals x plus 4, and 17 equals y minus 2. You could just realize that 17 is repeated. We can substitute one equation in for the other because of this. Y minus 2 equals x plus 4, because they both equal 17. So that's the basics of the substitution property of equality. Let's write it out. So where it says the substitution property, we say if A equals B, then A or B can replace its counterpart. So, for instance, if I tell you that, as an example, A equals 7 and B equals 2 times A, well, we can substitute in or change this A into a 7 because A equals 7. We could write it as, I'm just going to draw an arrow to show, B equals 2 times 7. That would be substitution. Finally, this one is not a property of equality, but it is a very important property. It's the distributive property. And honestly, this is one of those that makes more sense if I show a picture. Let's say I have 2 times x plus 3. The distributive property says, in essence, if you have a number outside of parentheses, you can then multiply it into the parentheses. This would be like 2 times x and 2 times 3. Both these are being multiplied, which is the same as 2x plus 6. The actual formal definition of the distributive property is a bit more complicated. It says, let A, B, and C be real numbers. In that case, or then, we can say that A times either B plus C or B minus C, so I'm going to write a plus or minus sign here because it could be either of them, is going to be AB, whatever we chose, plus or minus AC. So let's take these into consideration as we take a look at down here, the bottom of the page. When you solve an equation, just like we did in our original example here, boom, we are using the properties of real numbers without knowing it. Real numbers are just all the different types of numbers that we've talked about so far that exist. Things like 2 and 512, negative 7.5, or the square root of 2. All of those are real numbers. The properties that let you solve an equation for x also aren't restricted to just equations. Segment lengths, angle measures, things like that are going to be replaced with real numbers. Like if I'm looking at a segment and I tell you it's 6 units long, we can represent it using the real number 6. Angle measures we can look at and be like, oh, that's 72 degrees. Well, then it can be replaced by the number 72. We use these properties to write logical arguments about geometric figures. Eventually, these logical arguments won't just be arguments. They're going to turn into what we call a geometric proof. We're going to prove that something is true, other than saying, it looks like it would work. These properties are going to be called justifications or reasonings for those proofs. My recommendation is to make a running list. Anytime we use a property, a postulate, or a different justification in a proof, write it down. It's helpful to know what you can put as a reason for a proof. Let's flip the page and take a look at one such proof. So, this is called an algebraic proof because it's an algebra problem, and we're trying to prove that problem. When I say prove, I mean that we want to give each step a reason to exist. So, I'll give you an example. What tells us that we're able to take 7x equals 21 and divide by 7 on both sides? You might already know, but I'm getting ahead of myself. Let's start at the very beginning. The very beginning of any proof will always give you some information. You can't prove something if you don't have any information. Anytime you are given information, so it's going to be the first line of the proof, the justification we give is that it was given to us. We just write the word given. Every single proof that we do will start with the word given, because we have to start with some information, otherwise we won't know where to go. Take a look at the next line. It says 3x plus 2 plus 4x equals 23 minus 4x plus 4x. That plus 4x wasn't there before. So the question is, what lets us just willy-nilly add a plus 4x to both sides? Well, that's the addition property of equality. I'm going to abbreviate it for space reasons, but the most important thing is you cannot remove the of equality part. There are properties that aren't of equality that we'll be talking about. So there's an addition property of congruence, an addition property of inequality. We want to make sure we write the equal sign. So that's what let us do that step. Whoa. What happened in this step here? It looks like half the problem disappeared. Well, we see that the 3x and the 4x made 7x. And the negative 4x and the plus 4x made 0 and disappeared. So what justification can we give towards that? Since we combined like terms, that's what we really did here. We give the justification of simplify. That's what we did. We're telling someone, hey, once you get to this step, simplify to get to this step. Next up, we see that there is now a minus 2 in play on both sides. That wasn't there before. So what property lets us do that? Well, the subtraction property of equality tells us that we can subtract from both sides, as long as it's the same number. Since we subtracted 2 on both sides, that's the subtraction property. Again, how did we transform this? Well, 2 minus 2 is 0 and cancels out. 23 minus 2 is 21. So once again, we just simplified. What lets us divide both sides by 7? The division property of equality. I think we're starting to see a pattern here, right? Division property of equality lets us divide on both sides. So we divide by 7 on both sides, and look at what we're left with. We're just left with x equals 3. Again, we did that by simplifying 7 divided by 7 and 21 divided by 7. That there is our first complete proof. A proof is a geometric way of looking at things. I don't care how you solved it. I care about why you were able to do those steps. So this is an algebraic way of looking at this problem. This is a geometric way of looking at this problem. In general, though, we did a lot of steps that just said simplify, right? And some of these steps we could do in our heads. Like if we know that we're going to add 4x to both sides, can't I just cancel it here and just turn this into a 7x and skip this middle step entirely? I would certainly say so, right? In general, we skip these middle steps. We call them intermediate steps. If there is an intermediate step that does not add to the explanation, such as, hey, did you know that 3x plus 4x is 7x? We can skip it and just go down to the next one. If we skipped it, we would say given is the first one, and addition property of equality is what lets us get to 7x plus 2 equals 23. In general, the simplify steps are not required unless you're combining like terms. If you have a problem that starts you off with some terms you can combine, yeah, go ahead and combine them. Just write the word simplify for that reason. Keeping that in mind, I want us to see if we can try this example on our own. Notice I took out most of the fluff, most of the in-between simplify steps. We have to look at how we got from one equation to the other and write that as a reason. Again, I want to give you a hint. The first reason is always your given. Take a second to pause the video and try to see if you can complete the following proof. How did we do, everyone? As we take a look here, we started by distributing the -5 into the parentheses. That's how we made the parentheses disappear. After this, the -40 disappeared, and the other side became 70, so we know we must have added 40 to both sides. Following this, we want to get x by itself, so we have to get rid of this -35. We do that by dividing by -35 to get x equals -2. Let's take a look at example 2. Example 2 is a word problem. So, with word problems, I recommend underlining or circling important information as you read. We get a raise as a part-time job. To write your raise as a percent, use the formula P times parentheses R plus 1 equals N, where P is your previous wage, R is the percent increase as a decimal, and N is your new wage. We want to solve the formula for R, so we want to get R by itself using the 2 columns below. After that, it asks us, what is your raise, written as a percent, when your hourly wage increases from $7.25 to $7.54. Well, let's start off by ignoring that last bit because the first question is just asking us to solve for R. We really want to get R by itself. So, what can we do? as it turns out, there are two ways of solving this problem. After I show you the first way of solving it, I want you to see if you can solve it, knowing that the first step that we're going to be doing, after our given, of course, is the division property of equality. Don't try it out right now, but try it out after we do our first version. So, maybe you don't notice that you can divide. Maybe I see parentheses and I say, I want to distribute. While our original reason is because we are given that formula in the problem, the next thing we would write down is what happens when we distribute P. P times R is PR. P times 1 is P. So PR plus P equals N. And again, the reason why we said that we're allowed to do that is because of the distributive property. Nice. Well, how do we get R by itself now? We want to get rid of this P here. Remember, reverse PEMDAS says we always get rid of addition and subtraction first. So how to get rid of plus P? Well, we obviously have to subtract P. This is the subtraction property of equality. If we subtract P from this left side, the P will disappear, just leaving us with PR. If we subtract it from the right side, we would have N minus P. I also want to mention, while we don't want any of that fuzz in our proof here, we don't want to write down minus P inside of here, if you need to do some work on the side, like if you're like, oh, dang, I really want to see this the way I'm used to seeing it, feel free. Doodle on the side if you want. That's why I gave you space for it. Oops, this is PR, sorry. So, for instance, this is totally fine. Just make sure you then write it in the proof. Now, here's the last step. R is almost alone, but what do we have to do to get R all by itself? Well, this is P times R, so we have to use the division property of equality to divide by P on both sides. Again, this is one where you might find it more comforting to draw it to the side. So if we divide both sides by P, you would end up with R equals N minus P over P. But then we have to ask ourselves, is this simplified? We usually don't like multiple things on top of a fraction, so I want to remind you that whenever you have multiple things on the numerator of a fraction, but one denominator, you can split it into N over P minus P over P. See how the N over the P got its own spot and the negative or minus P over P got its own spot? Well, now we can simplify because P divided by P is just 1. Our equation here is R equals N divided by P minus 1. Done. Bam. We have finished the first part of the problem, solving the formula for R. Our rate, or our percent increase I should say, is our new wage divided by our previous wage minus 1. So all we need to do now to find our increase, our R value, is to plug in what we know. We know that our new wage is $7.54 an hour, and we know that our previous wage was $7.25 an hour. So we just have to solve this for R. When you plug this in your calculator, you'll get a decimal. R equals 0.04. So how do we turn that into a percent? By multiplying by 100, we get 4%. That is your raise. Good luck beating inflation with that raise, but I'm happy for you. Let's flip the page and take a look at some other types of proofs using some other properties of equality. Now, we are going to talk about 3 more properties of equality. Just keep in mind that these properties are true for all real numbers. That includes things like segment lengths and angle measures too. Let's take a look on our definitions page at the last 3. The reflexive property, the symmetric property, and the transitive property. I am going to give you the shortest possible definitions for these 3 properties. Then we'll go back to the page that has the examples on them to take a look. The reflexive property of equality says that something equals itself. Yes, indeed. Something is using the reflexive property if we're stating that it equals itself. So, for instance, 5 equals 5. They're the same thing, so that's reflexive property. It could also be something like a line segment. The length of AB is equal to the length of AB. Or even, the measure of angle 1 equals the measure of angle 1. All of these are valid uses for the reflexive property. The symmetric property of equality is a little bit trickier, but not much. In fact, not much at all. The symmetric property of equality says that if A equals B, then B equals A. It says that when you have an equation with an equal sign, you can flip it and it will still read the exact same thing. So, for instance, I could write x equals 2. I could also write 2 equals x, and both of those would be correct. I realize I'm writing in the wrong color, so I apologize. This also works with line segments. If I say that AB equals CD, those mean the length of AB and the length of CD are the same, then we can flip it, and it still means the same thing. Same with angles. If the measure of angle 1 is the same as the measure of angle 2, then we can flip it and say, by the symmetric property, the measure of angle 2 equals the measure of angle 1. Last but most certainly not least, we have the transitive property of equality. This one is very interesting because we've kind of seen an application of it. The law of syllogism applies to equations. Yes, indeed, the law of syllogism. This law was something that was introduced all the way back in 2.2. The law of syllogism says the following. If P then Q happens, and if Q then R happens, then because the Q is repeated, it'd be the same as me just saying, if P happens, then some stuff in the middle happens, then R happens. Because these two Q's are repeated, we can exclude them from a shortened version of our statement. So, examples of this in math might be, if 2 equals x and x equals 3y, then, since the x is repeated in the conclusion and hypothesis, 2 equals 3y. I might also trick you and give it to you in reverse order. So, for instance, if I tell you that CD equals EF and AB equals CD, you might be tempted to say, oh, the conclusion is that CD equals itself? No. The thing that's repeated is CD. So we get rid of the hypothesis and conclusion that's repeated and just write what's left over. AB is our first hypothesis, AB is our second hypothesis, EF is our first conclusion, AB equals EF would be using transitive property. This works with measures of angles too. If the measure of angle 1 equals the measure of angle 2, and the measure of angle 2 equals the measure of angle 3, then we can skip the middleman and just say that 1 is the same as 3. There are a ton more examples of this in the actual notes here, so I would recommend taking a look at this table here in the top left. This shows a lot more illustrative examples. Let's see if we can apply these rules and more to an equation that doesn't involve numbers. It instead involves the measurements of different angles. You reflect a beam of spotlight off a mirror lying flat on a stage, as shown. We are trying to prove that the measure of dBA, which I'm going to highlight in green, has to somehow, some way, equal the measurement of angle EBC. I want to get the elephant in the room out of the way. Yes, these two look like they are the exact same angle. No, that does not count as a proof of them being the exact same angle. Our human eyes can only be so precise. You can't zoom in and see, yes, this one is actually 0.002 degrees off, and this one is a little bit bigger. Can't do that. So we need to prove it. The first thing to notice is that there is a typo in this statement. So I'd like you to change this into the measure of angle 3, because that is a big typo that does change the entire problem. Our statement says that the measure of angle 1 equals the measure of angle 3. How do we know that? It's these congruency arcs. It says that these two angles are the same. But the reason we always give it first is because it is given to us. The diagram gives it to us. The measure of dBA is supposed to equal the measure of angle 3, which I will circle in green, plus the measure of angle 2. Now wait a minute. None of our properties we talked about this. That's because we learned something that this is a property of in the last unit. What property, or what postulate, more specifically, lets us add together two smaller angles that are next to each other to make a bigger angle? This is the angle addition postulate. I'm running out of space, but the angle addition postulate. Whatever. You all can read it. It says that when you put together two angles that are adjacent, they make a bigger angle. We can utilize different postulates from different units. In fact, we will need to solve some of these problems. The next thing that's written down is extremely strange, so I want us to consider it. It now says, instead of the measure of dBA equals the measure of angle 3 plus the measure of angle 2, the measure of angle dBA equals the measure of angle 1 plus the measure of angle 2. Uh-oh, that doesn't look right. According to the diagram, 2 plus 3 should equal dBA. Well, it's because we're using a different property here. Specifically, it's one of our properties of equality. What property of equality would let us change the measure of angle 3 into the measure of angle 1? Because that's really the only change. If we take a look at our first statement, it becomes clear. The measure of angle 3 is the measure of angle 1. They're equal to each other. So, we can substitute one in place of the other. Substitution property of equality. Do we see how, since measure of angle 3 and the measure of angle 1 are the same thing, that when we write down the measure of angle 3, we could also change it to the measure of angle 1 if we want? Well, now something interesting happens because there's another fact we can bring in. The fact that the measure of angle 1 plus the measure of angle 2 equals angle EBC, all in purple. Hang on a second, those two are adjacent angles that add together to make the bigger angle. This is just the angle addition postulate again. Nice. The last thing we need to do is to make a logical leap. We need to somehow figure out how the measure of dBA equals the measure of EBC. The first thing that I'd like to note is we should look at all the information where the measure of EBC is on this side here. It turns out there's one place right here. Okay, so we're definitely going to need to use this statement somehow. This statement also says that the measure of angle 1 plus the measure of angle 2 equals something. Do we see another place where the measure of angle 1 equals, or plus the measure of angle 2 is? Right above it. And the other piece of information that we're given is that piece we need down here, the measure of dBA. Ooh, I think I'm starting to see a pattern form. If A equals B and B equals C, then A equals C. What property lets us say this? The property that says if dBA is 1 plus 2, and if 1 plus 2 is EBC, then dBA equals EBC, is the transitive property. Remember, that was the one that said if A equals B and B equals C, then A equals C. If the measure of angle 1 equals the measure of angle 2, the measure of angle 2 equals the measure of angle 3, then the measure of angle 1 equals the measure of angle 3. It's the same general deal, just a little more complicated. That is our proof totally done. You might see me occasionally mark a square at the end of a proof. That is force of habit. You don't need to worry about doing that. That just shows that that problem is done. Example 4 is tougher for a couple of reasons. The first and most obvious reason is I did not give you the steps. Dun dun dun. No, instead I am asking you to write this proof. I want to give you some information before I give you some time to try it out and see if you can reach a conclusion, and then I will show you how I reached the conclusion. There are also many ways to reach that conclusion. I count at least 6. Keep in mind, we are trying to prove that PZ, this segment here, is equal to SM, this big old segment here. And all we are told are that PS and ZM are congruent. That is our given. Try this out, but don't be afraid to check in on the video. Pause here so you can brainstorm and come back to see the first step. Hopefully you've had a chance to try this out. If we really don't try these problems, there's no way we're going to learn it. So I want to show you that obviously we're given that PS and ZM are the same. We can't really do anything with that right away. Maybe later. What we can notice though is that PS plus SZ equals PZ, and that's one of our 2 goals that we want. We want to get PZ. So I'm going to write PZ is equal to PS plus SM. Or SZ, sorry. Didn't mean to mess it up there. What lets us say that PZ equals PS plus SZ? Well, that there is the segment addition postulate. Segment addition postulate. Again, another one from Unit 1. If you add two smaller segments, you get the bigger one. Don't we also want SM to be solved for? Personally, I think yes. I think we want to figure out exactly what SM equals. The good news is that SM is just SZ plus ZM. Again, that's the segment addition postulate. I wish to inform you that this next step is tough to see. Eventually, we do want to have PZ equals SM, right? That's our end goal. That's what we're going to want our last step of the table to be. But how do we jump from these three pieces of information to this? It's almost impossible, really, right? Not necessarily. Because consider here. PZ is PS plus SZ. We know PS is already up here. We would just need to add an SZ to make that work. But wait, similarly, SM is just SZ plus ZM. We would just need to add an SZ to this to make it happen. I think I see what we can do here. If we take our original statement here, PS equals ZM, and add SZ to both sides, now, doesn't the left side look exactly like the red equation, PS plus SZ and PS plus SZ? Similarly, doesn't the right side look exactly like the blue equation, SZ plus ZM, SZ plus ZM? What lets us just willy-nilly add SZ to both sides is the addition property of equality. That's the one that says you can add whatever you want to both sides as long as it's the same thing. I think I see how we can finish this problem. PZ equals PS plus SZ. PS plus SZ equals SZ plus ZM. SZ plus ZM equals SM. All we need to do is substitute in these values. We can substitute in PZ for PS plus SZ to get PZ. We can change SZ plus ZM into SM because that's what it equals. Our final conclusion is that we can use the substitution property of equality to substitute these out. So again, I want us to reflect on this because this is a toughie. It was an intentional toughie, a toughie that I gave of my own volition. We're starting with two segments, PS equaling ZM, the green ones up here. We then notice that, hey, our big mystery segment in red, PZ, is just PS plus SZ. Similarly, our big mystery segment SM is just SZ plus ZM. Looking at the equations, these two both have one thing in common. In fact, looking at the diagram, these two also have one thing in common. It's this segment here, SZ. That's the connector. That's the thing that'll connect these two ideas. So we recognized that if we added an SZ to PS and an SZ to ZM, then the left side would be PS plus SZ Hint, that's exactly what the red one says. And if we added sz to zm, it would look exactly like what the blue one says. It would say sz plus zm. That's what the blue one is. So we did that, because we're allowed to and no one's going to stop us. We added sz to both sides to make them look the same. After that, we notice that there are some things that are the same between these different equations, so we can substitute them into each other. Again, the matching parts were PS and SZ with PS and SC. So if they are the same, we can substitute in what it equals. We say that PZ is the same as this side, right there. Similarly, SZ plus ZM, I'll actually circle it to make it a little distinguished. These two are the same. So I can substitute in SM for that portion. This entire side of the equation becomes SM. And that is exactly what we wanted to prove. Thank you so much, everybody. Before we go, I want to remind you, this is a unit more than any other where practice makes perfect. We need to practice these proofs. Otherwise, I don't know that we'll be able to feel confident in how to do new ones. Try out some proofs, the ones that I gave you in the homework, and come to me if you have any questions. I believe in you. That said, have a fantastic rest of your night, everybody. Catch you next time.